So far we have seen the different functionalities which basically add the new value at the end of the single linked list, and which will basically add and remove the new values in front of the single linked list, right? And we have also implemented get functionality on a single linked list. Now that combining all these functionalities, we can write the insert operation on a singly linked list. So insert operation, what exactly it does is, it is basically used for inserting a new value anywhere in the singly linked list. For that operation, what exactly we will do is, we will basically take the index from the user and will also take the value that user wants to insert into the singly linked list. So here our job is to make sure that we are inserting a new node with the value that user has passed at the given index. So that is the main aim of the insert operation on a singly linked list. So remember that we have to take the index and we have to take the value, and we have to make sure that the new node with whatever the value that user has passed, we have to make sure that we are inserting a new node at the index that user has passed. So obviously, just like any other operation that involves index, right? The possible ranges for the index are basically, in the case of single linked list, are from 0 to length of the single linked list minus 1. But here there is a catch. The valid index for insert operation is from 0 till length of the linked list. Why? Because if you consider the single linked list that we have here, right, the indexes are 0, 1, 2, 3, 4, 5. But inside this single linked list, we almost have 6 values. That means the valid indexes are from 0 to 5. But the thing is, if the user passes an index 6, right, that means that we can insert a new node at the end of the singly linked list. That's why for insert operation, the possible range of index that user can pass is actually from 0 till the length of the linked list. And obviously, since singly linked list can store any type of the value in it, there will not be any validations on the value that user is passing. So the only validation that we have to make sure is if the index that user is passing is in the range of 0 to length of the linked list or not. Okay, so that is the basic definition of a insert operation. Now let's go ahead and let's try to understand what are the different cases that could arise when I try to implement the insert operation, and what are the functionalities that we can reuse for implementing the insert operation. So the first check would obviously be to check if the index that user has passed is invalid index or not. That means that when we are taking the index from the user, right, index is nothing but an integer value. So user can pass any negative values, and user can pass values that are greater than the length of the singly linked list. Obviously, in those cases, we will not be able to insert a new node into the singly linked list, right? That's why, as part of the first check, we will basically check if the index that user has passed, if it is less than 0, or if the index that user has passed is greater than the length of the linked list. If this is the case, we will simply return false, indicating that we are not able to insert the new node into the singly linked list. That is the first case. So besides this invalid case, all other indexes whatever we get from the user are basically valid cases, right? Out of those valid scenarios, the first scenario is if the index is equal to 0, right? The whatever the index that we are getting from the user is 0. That means that we already have a value at index 0. That means that when user asked us to perform insert operation at index 0, user is literally telling us that, insert a node before the existing head node, right? That operation is nothing but unshift operation, right? So we have already implemented this unshift operation, and we tried implementing it in such a way that it will handle all the scenarios already. That's why if the index is passed by the user is 0, what we will do, we will simply call the unshift operation with whatever the value that user has passed. So it will make sure that it is inserting a new node at 0th index. 0th index is nothing but before the existing head of the singly linked list. Let's assume that the value that user has passed is 10, right? So in that, let's say, again, let's assume 10 only. Now, unshift operation will make sure that it is inserting a new node, and head node also will get updated to the newly added node. So that is the first scenario when the index that is given by the user is 0. And as part of the third case, basically it is the second case where, let's say, the index that is given by the user is equal to the length of the linked list. That means that the last node is at the index length of the linked list minus 1, but the index that is given by the user is equal to length of the linked list. That means that we have to insert a new node after the tail node. That is nothing but a push operation that we have already implemented. In that case, if the index is equal to length of the linked list, what we will do, we will simply call the push functionality with the value that user has given. Let's assume that the value that user has given is, let's say, 1000 or 100, right? In that case, what exactly we will do, we will simply create a new node with value 1000, and we will adjust the next pointers of the current tail node, and we will update the tail node to the newly added node. Now if you see here, the index of the value 1000 will be 6. Okay, because we altogether have 7 values inside the single linked list, and the value 1000 is at the index 6. That's why you have to make sure that you are taking the valid values of the index from 0 till the length of the linked list. Okay, so that is the second scenario when the user, whatever the index that user has given, is the last index of the singly linked list. Now let's just try to understand if the index is any other index than 0th index, or the index that is equal to length of the linked list. That means that user wants to insert a new node with whatever the value after the index 0 and before the very last node we have on the singly linked list. So in that case, what exactly we will do is, we will try to reuse the functionality of the get functionality. But before I go ahead and I explain you the algorithm, right, let's just try to understand how the insertion actually happens. Let's assume that we have, let's say, 4 nodes inside our singly linked list. So the index will be 0, 1, 2, 3. Let's say the values are 10, A, C, let's say D are the values we have inside the singly linked list. And we have the head node and we have the tail node, and each and every node is connected to the next node like we have inside the singly linked list. Now here, as part of the insert operation, what I have actually given is, I want to insert a value at the index 2 by the value AB. That means that right now the index 2 has the value C, right? Now we have to make sure at the index 2 we are inserting a new node AB. That doesn't mean that we actually have to update it. We may have to make sure that we are inserting a new node altogether. That's why what exactly we will do is, with whatever the value that user has given, right, we will create the new node, and this node should be available in its before node, right? That means since we are inserting a node at second index, this node's reference should be available at the node that is at index 1. That means that next of A should store the reference of AB. Similarly, the next of AB should store the reference of C. In this way, this connection will be broken and new connections are being established. As a result, this AB will be available at index 2 and C will be available at index 3 and D will be available at index 4. So what exactly you have to observe here is, to insert a new node, first we have to have the nodes that are available at index 1 and the node that was at index 2 before we inserted the node, so that to the newly created node we can adjust the connections. If we generalize this, right, let's say if I am trying to insert the node at kth position, we have to have the node that is available at k minus 1th position and kth position, so that whatever the new node that we are inserting, we can adjust the next and next of the next nodes clearly. So in this way, to reuse the already implemented functionalities, what exactly we will do is, to have the access of this k minus 1th node, we will try to reuse the get functionality. Once we get that k minus 1th node, we will have the kth node also by simply doing dot next of k minus 1th node, and we will have a newly created node, and we can simply adjust the next pointers very easily. So that is the algorithm that you can use when the index that is given by the user is anywhere after index 0 and before the length of the linked list minus 1. So that is the otherwise index is greater than 0 and length of linked list. If this is the case, what we will do, first we will get the k minus 1th node. Once we get the k minus 1th node, this is k minus 1th node. Now the kth node will be this k minus 1th node dot next, right? Now with whatever the value that user has passed, we will create new node to it. Now this k minus 1th node next should be this new node that we have created. That's why k minus 1th node dot next will be equal to new node. Now we have adjusted the connection for the newly created node. Now to this newly created node, the next should be whatever the kth node that we had previously, which is available inside this kth node variable. That's why to update the next, new node dot next is equal to kth node. In this way, we are actually inserting the new node into the singly linked list. Just remember that this is not the update operation. We will have to insert a new node into the singly linked list. At the same time, we have to make sure that none of the values are getting lost while performing the insert operation. So for that simple operation is, these are the different cases, but this is the specific case where user is trying to insert a new node after index 0 and before the length of the linked list, whatever the index that user can pass. Okay, so that is the normal algorithm for insert operation. Now let's write the Java implementation of insert operation. For that, I'm going to go on to the Java file, that singly linked list.java that we have written. Here I will be writing a function called public boolean. Here I'm trying to define the return type as boolean, which will basically return true or false based on, if we are able to insert a new node at the index that is given by the user with the value also given by the user. So the return type will be boolean. Let me name the function name as insert. This function will basically take the index from the user, that is, it will be of type int, and it will also take the new value that should be used for inserting that specific node at the given index. Okay, whenever the index is involved, we know that whatever the index that user has shared could be a real value or could be a invalid value. In the case of insert operation, the valid range for the index is basically from 0 till the length of singly linked list. Why? Because the values or the nodes are already available from 0 till the length of singly linked list minus 1. So we can insert a new node at length of singly linked list index. So that's why the possible range is like what I have mentioned. So apart from that, still user can pass any unwanted index, right? So that means invalid index, right? So to eliminate all such cases, first what I will do is, if the index is less than 0 or if the index is greater than length of the singly linked list, that is this dot length. In that case, we will not be able to insert any new node with the value, so we will simply return false in this case. Okay, after this, if this is not the case, let's check for the other scenario. Whatever the node that we want to insert with the value that user has given, could be at the beginning of the linked list. That means at the 0th index itself, the user might want to, insert this value. In that case, if the index is 0, that means we are inserting a new node between the existing head node of the single linked list. That is nothing but unshift operation that we have already implemented. So we will reuse the unshift operation here, and the value is value. Okay, so this is the case where if the index that is given by the user is 0. In this case, we already have a head node and user wants to insert the new node at the beginning of the single linked list, that is 0th index itself. In that case, this is nothing but unshift operation, so we have used the unshift functionality that we have already written. If this is not the case, whatever the index that user has given, if it is exactly the same as the length of the array, the possible valid range of the nodes are basically from 0 to length of linked list minus 1. But if we are trying to insert a new node at the index that is equal to the length of single linked list, that means at the end of the tail we are trying to insert a new node. That is nothing but push operation. So if that is the case, that means if index is equal to this dot length, then we will simply use this dot push, okay, with the value that user has passed. Okay, in this case, when index is 0 also, since we are able to insert a new node at the beginning of the linked list, we will return true here. Okay, similarly in the case of if it is similar to length of linked list also, since we are able to insert the new node with the value that user has passed using the push functionality that we have already implemented, in that case also we will return true. If this is not the case, that means that we are trying to insert the new node anyway after 0th index and before the length of the linked list, right? For that, what we will do is, first let's assume that the user wants to insert the new node at index 5. So first what we have to do, we have to go till the node that is available at index 4, right? So first we have to get the node at n minus 1th index. So for that, I'll simply reuse the get functionality. The index that I will pass for this get functionality is index minus 1. Okay, here what I will do is I'll simply read it as node. Okay, now once I have, this is node at the index minus 1th position. Along with this, we have to create a new node with the value that user has given, right? So for that, what I will do is I'll create a new node object, new node equal to new node of the value that user has passed. Now we have the node at index minus 1th position in node value, and the node that is at index position will be the node dot next. So what I will do, node dot next I will take, let me just take it into node next node. Okay, let me just take it as a next node variable. Now what we have to do, we have the node that is at index minus 1th position in node variable, and we have the new node. So whatever the new node that we want to insert will be the next of the node that is at index minus 1th position. So what I will do is node dot next will be new node dot new node. Okay, now we have updated the next of the index node at index minus 1th position, and whatever the remaining nodes were there, that is part of next node, right? So this will be the next of the new node that we have inserted. So new node dot next is equal to the next node. Okay, here since we are trying to insert the new node manually, right? For that, simply I'll increment the length to this dot length plus 1. Okay, in the case of unshift and push operations, they themselves are taking care of the length, so we don't have to increment them manually here. But here, since we are trying to insert the node specific to this case, that's why I'm incrementing the length by 1, and we will have to return true, indicating that we are able to insert the node successfully. Okay, this is the implementation of insert function. So as part of the first case, whatever the index that user has given could be invalid, so we will simply return false. If the index is 0, that means that we are trying to insert the new node in front of the head node itself. That means 0th index itself. In that is nothing but unshift operation. So we are reusing the unshift operation here. If at all the index that user has given is equal to the length of the linked list, that means we are trying to insert the node after the existing tail node. So that is nothing but push operation. So we reuse the push operation. Otherwise, if that is not the case, we will have to reach the node that is prior to the node that is at index position. So we read that value and we have the next nodes available also in some variable. Now with the new node that we have created, we've inserted and we've adjusted the next pointers like you see on the implementation. Okay, now let's try to call these and see if we are able to insert the values or not. So for that, let me just traverse function first, and after that let me call the insert, and the index is 3 and the value is Sai. In that case, right now the index 0 is 10, 1 is codingpal.arg, 2 is true. If we try to insert a value at index 3, that means it will be Sai and the value at 4th index will be 10.0. So if we execute this line of code now, ideally we should see the result. So run as Java application. If you see, before inserting as part of the traverse, we've got 10 codingpal.arg true 10.0. After insert operation, we printed line separator that we've got here. Now again we perform traverse. If you see here, 10 codingpal.arg true Sai. So whatever the Sai value that you inserted is at index 3. 0, 1, 2, 3. Okay, which is exactly what we have discussed. Similarly, if you observe here, head is at 10, tail is at 10.0, and the total number of nodes are, after inserting Sai into single linked list, it is 5, which we have got. Similarly, let's assume that whatever the node we are trying to perform is equal to the length of the linked list, that is 4. So if I pass 4, ideally the tail should become Sai, because that is the last value that we are trying to insert, and we are using push operation in our implementation. So if you see here, the last value that got inserted at index 4, which is equal to the length of the linked list at that time, and if you can observe here, we've got the tail also to the node that contains the value Sai, and the length is also becoming 5. Okay, this is how we basically perform the insert operation. Right now, let's try to perform the insert operation on a empty single linked list. In the case of empty single linked list, I will pass index as 0, or non-empty single linked list also, it's fine. In this case, both head and tail should be pointing to the node Sai, and it should have only one value. If I execute it, okay, do you see, as part of the before insertion we tried traversing, right? There were no values, so we did not print anything. Line separator, and after inserting, traverse got Sai and head and tail are at same node. Okay, so as part of this, the logic basically went into this shift logic because the index that we passed is 0. Okay, this is how we actually implement the insert operation inside a single linked list at a given index with the value that is passed by the user. Okay, so most of the logic here, we reused all the functions except the case that where we are trying to insert the value after the index 0 and before the index that is less than the length of the linked list minus 1. Okay, besides that, of course, even in that case also we reused get, but there is a little logic that you have to make sure that you are adjusting the next pointers clearly. Okay, now that we have implemented the insert operation, let's just try to analyze the time complexity and space complexity of the algorithm that we are following for inserting a new node into the single linked list at a given position by the user with whatever the value that user has passed. And this also, let's just try to divide and analyze in best case as well as worst case. Okay, so when will the best case of insertion operation will occur? Let's assume that we have some number of nodes that are available inside the single linked list. So as part of the best case is something that it will simply occur with a simple update operation. So in the case of insert operation, whenever the user is trying to insert a new node in front of the existing head node, that means that at the index 0 itself, that is a simple update operation because we already have the head node. We are simply using a unshift operation performing the same insert. Similarly, if the user, whatever the index that user is passing, if it is the index that is equal to length of the linked list, in that case we are simply reusing the push functionality. In these two scenarios, since we had the access to the head node and tail node, with the simple update operations, we were able to add the new node into the single linked list. As a result, that is the best case of a insert operation on a single linked list. In that case, obviously both unshift as well as push operations will take only constant amount of time. So we can say in the best case scenario, the time complexity will be order of 1. Now, when will the actual worst case scenario of the push functionality insert operation will actually occur? Let's assume that we have some number of nodes available inside the single linked list. Here, let's assume that there are n number of nodes. So this is the head node and this is the tail node, index 0, 1, 2, 3. Now, just assume that this is the nth node. Now, let's assume that whatever the index that user has passed, right, if it is equal to the n minus 1. So we already have the n nodes available in the single linked list, and the index that user has passed is n minus 1. That means that user wants to insert the node at the very last index in the singly linked list. In that case, we have to call the get functionality by n minus 2, right? In that case, get function to get the node that is at n minus 2th index, we have to run a loop for n minus 2 number of times. So in that case, that's why the worst case time complexity will be order of n minus 2. We can simply say order of n. Now let's just try to understand the same thing in terms of space. So if you already know when is the best case, right? When the user is trying to insert the node at the beginning or at the end of the single linked list, that is the best case scenario. In both those scenarios, we will simply reuse the unshift and push operations, which will basically make the necessary adjustments in a constant amount of memory. If you remember the time and space complexities that were involved in the push and unshift operations, right? They were constant. As a result, in the best case scenario, the space complexity will be order of 1 only. Now let's just try to understand the space complexity involved in the worst case scenario. Here altogether we are calling the insert operation at the index n minus 1, right? And we are making the reuse of the get functionality. And if you remember the time complexities and space complexities involved in the get functionality, right? We will simply reuse a single variable for reaching the node at any position in the singly linked list. As a result, even in the worst case, the get functionality will have a space complexity of order of 1 only. And once we get the node also, after that, we are making 2 next pointer adjustments, right? And these next pointer adjustments will obviously be a simple assignment operations, and they will take only constant amount of memory. As a result, the overall space complexity in the worst case scenario of insert operation on a singly linked list where you are trying to insert the node at the very last index will be order of 1 only, even in the worst case scenario. Okay, so that is the time complexity and space complexity analysis of a insert operation on a singly linked list.